I have a radical equation I want to show you today. And these normally are kind of difficult to solve, or at least tedious. But this one turns out, you're told over and over not to square away on something like this, subtract one radical from the other side. But in this case, you can square away, and it's because of a special feature of the individual radicands. These two radicands are similar, and you can use the difference of two squares actually to simplify. So it turns out, even though it's tempting to subtract one from the other then square, bring this to the other side and then square, it's okay to directly square right here, which I thought, that's why I've decided to show this. But now, notice that our solution, we're given that there's going to be a single real solution. And notice that solution would have to be greater than 0. Okay, x has to be greater than 0. There's no doubt about it. The range of the square root function is positive. And also, when you substitute 0 in on both sides, you get 0 on the right-hand side and 2 square root of 5 on the other side. So x must be greater than 0 simply because substituting 0 does not provide a solution to the original equation. Now, so we just start out by squaring both sides. So again, that's a little counterintuitive. That's what you would try if you were first learning this, but you kind of learn some tricks over the years. And normally, like I said earlier, you're better off subtracting one of the radicals to the other side and then squaring, and that usually simplifies things. But in this case, it works out just fine. Notice that this would be, if you're thinking of this as a plus b squared, the a plus b quantity squared, this would be your a squared right here. This guy right here would be a squared, and then b squared right here. And then, of course, this part over here would be your 2ab, and you're just putting the radicals together. So remember, that's just equal to, this whole thing is equal to a plus b quantity squared, right? So that's exactly what we did right here. We just squared away. And notice how we get 9x squared over here, because that's what when you just square 3x, you get 9x squared. But so now this works out relatively nicely at this point, because notice that these 4x terms cancel out. These 4x terms cancel, and so you just get 2x squared plus 10 right here. 2x squared plus 10. All right, and then I left this piece right here, and then equals to the 9x squared. All right, now, so to get to this next line, all we did was just subtract 2x squared and 10 from this side to get 7x squared minus 10. All right, so everything's good right here. Okay, now it still looks like, oh no, man, what are we going to do? But we square again, okay? Now, when you square this object right here, the radical goes away. You're left with a 4, right? You're left with a 4. But notice that this piece right here is just, when you expand this out using the a plus b result, this would be x to the 4th. I'm just writing just this part right here, folks. You would get x to the 4th power. Again, we're just squaring this binomial right here. And then 5 would multiply against x squared twice. And so that's 10x squared. Okay, and then plus 25. And that's, I'm just expanding that out because I left that step out sort of, that explains if this part is equal to this, well, this 10x squared right here minus this 16x squared is the minus 6x squared that you see right here. Okay. All right, so that's all, it's all working out pretty good. Now, what makes this work, and not just any of these forms are going to work, but notice right here we have 4 times 25 is 100. And now when you expand this out, when you square 7x squared minus 10, you get this part right here, 49x to the 4th minus 140x squared plus 100. This is what happens when you, let me just write it directly above. 7x squared minus 10 quantity squared. Okay. We've already seen what happens when we square this piece, but when you square this piece right here, that's supposed to be a parentheses there, folks. 7x squared minus 10 quantity squared gives you this term, and this term. But what happens, the 100s cancel conveniently, and then we end up with this result right here. 45x to the fourth minus 116x squared is equal to 0. And again, folks, if these constants if the 100s had not canceled, the 4 times 25 is 100, 100 over here cancels, we would be left with a quartic equation with some missing cubic term and missing x term, but still it'd be a quartic that you wouldn't be able to solve, you know? So now, so we have this equal to 0. Now, if you divide by x squared, you end up with this result right here, okay? You end up with x squared is equal to this. Now, you may say, don't you take the plus and minus square roots? Yeah, well, you do technically, but we already know that x has to be greater than 0 just from the original problem statement, right? X must be greater than 0. Just think of it like this: if x were less than 0, you would have 3x over here being less than 0. Okay. Now, I don't mind personally. I like just leaving the problem like this. But notice you can rewrite this if you want to. This is what they call rationalizing the denominator. You can rewrite this as the square root of this is 4. This is 2 times 2 times 29, I believe. Yeah. So you would have 2 squared. 4 times 29 is 116, folks. So you'd have 2 squared over 29. This is where the prime factorization is kind of nice. It actually has some practical value. Now this is also what 3 squared times 5. So you would have 3 squared. Yeah, I want you to know that this is really a totally legitimate way to leave the answers. Just a lot of people, when they're teaching this in intermediate algebra and in college algebra, for example, they teach you how to rationalize the denominator where the denominator is no longer in the scope of the square root. And so anyway, this is equal to, let me come back over here because I think I'm going to run out of room. So this would be equal to 2/3 Okay. Again, y'all, you can take the square root of 2 squared over 3 squared. It's just 2/3 times the square root of 29 over 5. Okay. Now, a very common approach here is just to multiply top and bottom by the square root of 5. That'll make the bottom part just equal to 5. And so this would actually be equal to 2 times the square root of 145. See, 145 doesn't have any perfect square factors. Now, again, we multiplied top and bottom here by the square root of 5, but that just gives you 5 on the bottom. So this would be still 2 over 3. I'll just show this step. This is always kind of tedious and nobody really wants to do it. But so you have 5 there, right? Okay, folks, and then that's equal to 2 over 15 times the square root of 145. And a lot of people perceive this as a better way to write the problem. I mean, I guess I can, at least 2 over 15. You have some idea what that number actually is, but some people quarrel about these things. It's not that big a deal in my humble opinion. But so you get something that looks completely different, okay? You go, what? You mean this is equal to this? But you can check it out. If you put this into your calculator and put that in the calculator, you'll get the same answer. So this would be the so-called, the final answer in many people's, if somebody's teaching intermediate algebra or teaching people just, college algebra, intermediate algebra, this is called rationalizing the denominator, sort of a misnomer in my opinion. You're just creating a circumstance where you're multiplying a fraction times just a square. And this is kind of, the square root of 144 would be 12, right? And so at least you would know this number was approximately, maybe that's the reason they do it, just discover that, right? Y'all, 145 is approximately, the square root of 145 is approximately 12. And so this would actually be approximately 24 over 15. So this has been a whole other video right here, but so like I said, a lot of people just would leave the answer this way for this kind of problem. It doesn't really make any difference, but this is the answer in the back of the book type of thing you would see. All right, y'all, I hope you enjoyed. Thanks for again.